Okay, so I'll talk about statistical contribution to historical linguistics, and this is some work I'm doing with Jake Atibaia, my advisor at CMU. And so, first I'll talk about what historical linguistics is, and it's mainly the field of linguistics that studies language change over time. So, for example, we could look at how Portuguese looked when Brazil was discovered and see how it evolved over time. But we can also look at a different question that we're interested in this work, that is which languages are related. So we say that two languages are related if they descend from a common ancestor, right? And we call the common ancestor a proto-language. And we're interested in discovering what are the proto-languages and what are the relationships between languages. So here's an example. We know that Italian and Spanish are related, and both of them come from Vulgar Latin in the past, right? And they are both part of the Romance family. And English and German are also related. The proto-language is Proto-Germanic. They're both part of the Germanic family. And on the upper level, Germanic and Romance, Proto-Germanic and Proto-Romance are also related, and they're both part of the European family. So the relationships between languages are typically organized as trees. And a common challenge when you're doing historical linguistics is that not always do we have written evidence of the proto-languages. So even though, for example, for Portuguese and Spanish, we have Latin, a written form of Latin. For English and German, we don't have any written form of Proto-Germanic. So the question is how to find these relationships between languages without a written form of the proto-language. And the typical thing that is done by linguists is the comparative method. And they say that two languages are related if their features are similar, or if the similarities between the features can be explained by a regular change. And I'll talk about now what a regular change is. So, for example, in this table, you can see that Italian, Spanish, and Portuguese are similar because the first letter is all P for all of the meanings, right? And we know that English and German are also similar because the first phoneme is F for all of the meanings. But English-German is also similar to Italian, Spanish, and Portuguese, and their dissimilarity can be explained by a regular change. That is, all F's become P's, or all P's become F's, right? So this gives us evidence that English and German are also related to Italian, Spanish, and Portuguese. And even though the comparative method works fine for languages which are related more recently in time, it's not a quantitative method. It's like a painstaking method in which the linguist compares feature by feature the different languages. So, and it doesn't quantify the evidence. So as we go further down, closer to the root, evidence became shakier, and we don't have certainty about what we're concluding anymore. So in principle, we would like a method for quantifying the evidence and for combining different types of evidence. And given this challenge, many people have proposed quantitative methods to evaluate this type of linguistic evidence. But the problem is that most of these methods don't take regular sound changes into account. So that's what we're going to do, we're trying to do in this work. And the outline of what we did is we are going to, in this first stage, only use phonological information, that is, information about how the words are pronunciated. And we will try to incorporate regular changes into our model, and we will make a model for how, evolutionary model for languages. So we'll provide a model for how from the root language the words evolve into the model languages. And therefore we'll try to quantify the evidence that different languages are related. So in order to present the evolutionary model, I'll first have to provide some notation. Sigma stands for the set of all IPA symbols, and that's just an alphabet for phonemes. M is a set of meanings, and tau is a fixed tree of language relationships. So the relationships we can express using a tree. And our strategy to explain the evolutionary model is to first describe how words go from the immediate ancestor to the modern language, and then using this simple evolutionary model will generalize for how the words evolve in the whole tree. So in order to talk about the word evolution in a given plural language, we have to first ask what types of regular changes happen. And one type of regular change is the unconditioned sound change. And it's very simple to explain. All given phonemes in the plural language change to another phoneme in the modal language. So for example, we denote by A becomes B, and that means that all phonemes in the plural language that are A become a B in the more recent language. So for example, in this table, we have P becomes F, or F becomes P. We don't know, just looking at the table, we don't know exactly which one happened, but the table is like good evidence that one or the other happened at some point in the past. And this is a part of a well-known sound change law that is called Grimm's law. So Germanic languages, English and German, went through a sound change. And another important thing about sound change, unconditioned sound changes, is that more than a single one can happen in a given language. So, and when more than one occurs, the order in which they occur is important. So for example, what we get by applying A becomes B and then B becomes C is different from what we get by applying B becomes C and then A becomes B. So for example, in the latter case, we can have both C and B in the modern language, and in the previous case, we can have only C. So they are different. And since they are different, we have to take the order into account, and we model all the sound changes that occur in a given language as a vector of unconditioned sound changes. And we denote it by UI. So here it's just an example of what happens if you apply sound change UL to the phoneme P. And here we are applying B becomes P, T becomes theta, and P becomes F to the phoneme B. And we just go through the chain and find out that it becomes F. And that's also another example of Grimm's law. And finally, now we're in good shape to explain how words evolve in a single branch of the tree. And we denote L by a language by L. P of L is the immediate ancestor. UL is a sequence of sound changes. WLI is just the first phoneme for meaning I in language L. And lambda PL is the frequency of irregular outcomes. So I'll explain now. A regular outcome is just what you get when you apply a regular sound change to the phoneme W. And the irregular outcome is when you have some kind of noise. So for example, you can have a different type of sound change that is not unconditioned, or you can just have some kind of change that you cannot explain due to, for example, in languages, sometimes you can get a sound that a meaning that a sound that changes from different meanings, so that wouldn't be explained by the model, and that fits into irregular outcome. And then we just say that the phoneme is generated by some kind of noisy distribution. So, putting all that together, we generate a random variable that says if that given meaning was generated by a regular change or by an irregular change, and that's the random variable outcome, and it depends on the parameter lambda. And in case it was generated by a regular outcome, then we just generate it as a uniform among all IK symbols. And if it wasn't generated by a regular outcome, then we generate it according to the regular outcome, which is an unconditioned sound change. But then, in order to generate this model, we were treating the sound changes that occur, the frequency of irregular outcomes, and the words in the proto language as known, and they are not known. So now we'll talk about how these random variables are generated according to our model, and how to do inference on them. So there are two types of languages in the tree. One that has an ancestor, and there's a single one that has no ancestor, which is the root of the tree. And according to this model, according to the model that we're using, if you're in the root, then all the words, all the first phonemes for the words are generated according to a multinomial, and the multinomial will follow, F sigma is just the frequency of this multinomial for the root. this parameter is not really important. And then for the frequency of irregular outcomes in each one of the languages, we just treat them independently and use a standard beta distribution so that we have a conjugate. And finally, to generate the unconditioned sound changes, we try to incorporate the principles of phonology. And in order to do that, we just treat these hyperparameters. A sigma is just the frequency of sound changes that happen in languages in general that have antecedent sigma. And C sigma 1, sigma 2 is the frequency of sound changes that have antecedent sigma 1 and that change to the consequent sigma 2. And then for each one of the languages, we have this pair of parameters, AL sigma, that is 1 if there is a sound change which has antecedent sigma in that language, L, and CL sigma is just the consequence that this antecedent sigma goes to for that language L. And we just generated in the natural way, so A sigma and C sigma just come from betas and Dirichlet since they are all probabilities. And AL sigma and CL sigma come from the Bernoulli and antinomials with their respective parameters. And finally, we say that the sound change is S, L sigma, and the model generates each one of the unconditioned sound changes that we have in the language, and we say that all possible orders have equal probability. So now that we have all of these parameters defined and how to generate them, the full model is specified, and you can do inference on the model. And it can be simplified. This is a slice of the model in a given branch of the tree. So we have the frequencies of sound changes that occur, and that's used to construct the sound changes that happen in the language L. Then we have the words for the proto-language. And then the frequency of irregular outcomes are used to define which words in that language suffer irregular or regular outcomes. And then using outcomes, the proto-words and the sound changes for language L, we can finally construct the words for language L. And we built a model so that F, A sigma, C sigma, and lambda all have conjugate distribution. So we can just do a metropolis in which we update each one of them to a Gibbs sampler. And then UL and WL are a little bit more complicated because they're very correlated and the distribution is not conjugate for them. So we sample from them jointly and do a metropolis. And then you can use the fact that usually if you only make a single sound change, then most of the conditional distributions for words remain unchanged, so we don't have to resample from them. And that's a trick we use to get some efficiency. And then finally, once we have a model, we have a question about what data fits the assumptions of our model. And what we are assuming is that, in general, words that come from branches that are disconnected are independent, and different words from the same language or for different meanings are also independent. And there's a very simple counterexample to this. If you take the singular and the plural form of a word, we imagine that the first phoneme is going to be the same. So we have to select words that are farther apart in some way. And in order to do that, we used a Swedish list, which was developed by this linguist. And he tried to build 200 words that are very resistant to borrowing and also to change. And we are using these 200 meanings, so that then the conditional independencies in the model can be justified. So we just transcribed the Swedish list for different languages into IPA. And for our initial results, we use Indo-European languages because the relations in this family are well known, and so we can test our model better. And we are using Dutch, English, German, Greek, Italian, Portuguese, and Spanish for this first round of tests. And we can obtain the data from Wiktionary.org. And to test the model, we considered these two scenarios. first we considered some simple trees in which, for each one of the 28 pairs, we constructed a simple tree which only had a root connecting these two pairs, and we used this to find how related these different languages are. And we also constructed this simple tree with 4 languages to find the sound changes. And in our initial test, what we found, this is the first scenario in which we are taking the different pairs of trees. And here we are just doing a multidimensional scaling on we are treating the frequency of irregular outcomes as a measure of distance between languages. And then in this picture, we are just projecting this distance into a two-dimensional space. And we can see that there's like a cluster of Spanish, Portuguese, French, and Italian. That is the Romance family, and it's very far apart. We have Dutch, German, and English in the Germanic family, and we have Greek that is in its own family, the Hellenic family. So it's doing well for these big families, but it's not doing so well in identifying which languages are closer in each one of the smaller families. So that's a part that we are considering now at this point. And in the second scenario, in which we use English, German, Italian, and Spanish, we try to identify what sound changes occur in these languages. And most of these sound changes are correct, but we have a problem. So for example, it identifies that in Italian we have theta becomes t, but what actually happens is that t becomes theta. And this is a sort of a problem. If we, for example, if we remember the initial table in which we didn't know if f becomes p or p becomes f, sometimes the data doesn't provide any evidence to distinguish among these different scenarios. And actually linguists know which sound change happened, t becomes theta or theta becomes t, based on the phonological principles they know. That's not based on evidence, on this type of evidence. So, given this challenge, what we are trying to work on now is how can we incorporate the prior knowledge that the linguists have about the direction of sound changes, so that we can distinguish between t becomes theta and theta becomes t, for example. And we also did a sensitivity analysis on our model to understand where the prior is being important. For this first test, we used the uniform prior, and it does bad in some cases, as I showed in the previous slide. And we found out that it's very robust for the priors on the frequencies on the root language and for the irregular outcomes. And it's simple because the effective sample size is the number of meanings that we have. And usually we have about 200 meanings. But the results are very sensitive for what types of sound changes happen. And the types of sound changes are given by the variables A and C. And that happens because the effective sample size is close to the number of languages. And here we are using just a couple of them, 4 or 5. So what we are working on now are extensions to this model. First, we are trying to elicit the priors for the types of sound changes which happen. And that is, we are trying to find out the hyperparameters for A sigma and C sigma 1, C sigma 2. And since it's just a Dirichlet and a beta, we can use the standard elicitation methods that we can find, for example, in O'Hagan. The big problem is that we have about 500 hyperparameters. So we are developing a method with the linguists that we're working with about how to elicit all these hyperparameters. We've been doing this for a month now. Let's see what happens. And the second part is to extend this model to also do inference on the tree, the evolutionary tree. So for now we are treating the tree as fixed, and then we infer what types of sound changes occurred and what are the proto language, what are the proto words for the proto languages. But we also want to do inference on trees. And then we are using a method we are trying to implement a method that was developed by Atibaia, which is more or less heating the tree so that it mixes quicker. And that's what we are trying now. Thanks. That's about it.